What is a queue? How do you implement one? What is a heap and how do you use it? And what are real-life practical applications of these two concepts? Hello, welcome back to my channel, and today we are going to discuss queues, in particular priority queues. We will see also what is a heap, and we will also see what is the correlation between queue and heap. First of all, what is a queue? A queue is an abstract data type, an ADT. An abstract data type means that it has no particular implementation, but it describes a behavior. That's why it's called abstract, and you are free to use, any implementation you believe is efficient as long as you satisfy the behavior requirements. We will see exactly what that means. Essentially, a queue is a collection of entities which are kept in a sequence, and you can modify the queue by adding to the back of the queue or by removing from the front of the queue. It's also a FIFO mechanism, so the first one to go in is the first one to go out. So if for a more concrete example, just think of the people waiting in line at the Apple store. They are processed in the order in which they arrive. So essentially queues are used everywhere where there is a need for entities to be stored and processed later in some order. Priority queue is a type of queue, and this is what we will implement today. And essentially, it's a queue where each element has an additional priority property. In a standard queue, the elements will exit the queue in the same order in which they arrive. In a priority queue, the order in which elements are being enqueued doesn't matter. In a priority queue, the element with higher priority is returned before the one with lower priority, even if the higher priority element arrived later in the queue, right? So this is not a FIFO, it's a priority order. We will use the heap data structure to implement the priority queue. What is the heap data structure? A heap is a tree data structure which must satisfy the heap property. The heap property is also called the heap invariant. The heap property is based on a type of heap. There are two types of heaps. There are max heaps and there are minimum heaps. Max heaps, so if you picture a tree with multiple nodes, the root node, the one that does not have a parent, always has the highest value in the tree. And as you go down from that root node, each node has a value higher than all its children. This is the heap property. This order has to be respected so that we can consider that this tree is an actual heap. The min heap is exactly the other way around. All the children have to have values that are greater than the parent. So that means the root node has the smallest value in the entire tree. So when are these heaps actually useful? When you need, for example, to repeatedly access or remove the object with the highest value. We will be using the heap data structure to implement a priority queue abstract data type, and we will simulate an emergency room in a hospital where the patients are being handled. They are injured and they have to be handled in the order of how severe the injury is. Okay, let's begin by writing some code. So first of all, we will do a simple queue implementation. So before we dive into the priority queue, we will implement a simple queue, touch simple queue, let go. And then we will have a test file, of course, to test our queue, touch simple queue test, let go. So we will have package declaration first of all. As usual, our queue essentially is a struct which has some items of type pointer to anything. In order to consider this a queue, we need to support these two operations that we mentioned before. So we need the enqueuing and the dequeuing, right? So the enqueuing adds to the back of the queue, dequeuing removes from the front. So we're going to say func, and this is applicable for queues. This is called enqueue. It receives an item of any type. And basically what happens is that the items are being appended with the address of this item. Very simple method. We also need to remove from the queue. So we will have a function which is usable on queues, which is called dequeue, and this returns whatever we are dequeuing. First of all, we need to check if there is anything in the item slice. If no, so if the length of items is 0, then we don't want to return anything because there is nothing to return out of it. First, it will be queue.items of position 0, right? So we definitely have a first item because we have handled the case already when there is nothing in the queue. We just slice from the position 1 to the end. Queue.items is queue.items from position 1 to the end, and that's written like this, from position 1 to the end. Now that we have reassigned our items, we have essentially removed the first item. We still have it here in this reference. We just return the item. So we are returning the first. Oh no, this is a pointer, so we need to dereference it. Let's add some explanations here. So very simple. Now we have satisfied the requirements of the queue. Now let's do some tests to make sure that this actually works. We go into our test file, and here we need to declare a package, of course. And then we have a function test and queue and dequeue. We save the file, it imports the testing. Essentially, when we have a queue, and then we enqueue the string, let's say A, and then we enqueue another string, let's say B, and then we want to dequeue them. We want to just make sure that they are dequeued in the expected FIFO order, right? So actual 1 is queue.dequeue, and actual 2 is, right? And since this is a FIFO, we expect that the first actual 1 contains element A. If it's not so, if actual 1 does not equal A, then we have an error, right? The second one should be, of course, B, and if it's not so, then we have an error. If actual 2 is not B, then we have expected second element removed to be B. Okay, let's test. Go test. We see that the test passes. So this was a very simplistic implementation of a queue. There is nothing that interesting, just so we understand how it actually works. Now let's go and do something a lot more interesting. Let's dive into something called a priority queue. We understand what a priority queue is. It's a queue that has another property called priority, and that property decides the order of exiting from the queue. But to understand how to implement it, we need to understand the heaps. So let's begin by adding a file called, and then we will have test file. Right, so basically we should implement here a system that simulates an emergency room in a hospital where the patients are handled in the order of how severe their injuries. So let's do that. Priority queue, let's say package queue. And then we have, let's say, type emergency room, which is a struct. And it has a queue, let's call it patients queue. No, it's not a queue, it's supposed to be a patients queue. So I could just create it above here, but I will create a new file just for the sake of having a bit more organized code. So let's create patients queue.go, and we have package queue, and then we have type patients queue, which is essentially just a slice of patients. Let's first define what this means, what this type is. Touch patient.go. A patient, essentially, so package queue. So what is a patient? A patient is a struct, and the patient has a name, of course. And then the patient has injury, how severe, let's say, severity. And then let's call this patient severity status. Okay, let's create this type. So we have type patient severity status, which is just an integer. No, integer. And then these integers should just be constants. So we make a sort of enum here, a list of constants. We have mild injury, which is a patient severity status, equals iota, a way to just declare a sequence of integers. This means this is 0. Then we have moderate injury, and then we have critical injury. I don't think we need the word injury. Maybe let's just simplify. We can even change this, because we know it's about patients. So now we save this. All right, so now that we have these patient types declared, we need to solve the queue. So this is our priority queue. Okay, in order to implement this patient's queue, we know that we need to satisfy the queue property. We need to add to the queue, and we need to remove from the queue. So we can say func, let's say push patient data, which is some interface. This is, of course, valid on a queue, patient's queue. And then we will have another function, func pop, and it returns an interface. And let's say return nil for now. Return. we will get back to these methods and we'll implement them. These methods are required for us to be able to implement the priority queue. If we go back to our priority queue, right, we have this emergency room here. Let's try to make a constructor for it. So we have a func new emergency room, which returns a pointer to an emergency. So now what we want to do is we said here that we want to implement the priority queue by using the heap data structure. So Golang has this package available. What we need to do is to say heap.init, okay? Then you can see it will import from container heap. So we do this, now it has imported. We want to essentially call this. We have tried to initialize the heap, but we have some errors. Let's see why. So if we look in the heap init, we put the mouse cursor over and we tap F12. We go to the package. The Golang packages are extremely well documented, so you can read here. The init basically handles the heap invariants. Here we can see the signature. The way to use the heap init is to pass something that satisfies this signature. And what is the signature of the heap interface? It needs something that implements the sort interface and then implements, which accepts an interface, and then it implements a pop method which returns an interface of any type. So if we take these two things here, so let's just copy this from the package, right? So if we go into our patient's queue here, go to definition, we remember that we have these methods here. What we need to do, we need our patient's queue to also implement the sort interface. Because if we look here, cannot use ER variable of type pointer to emergency room as heap interface value in argument to heap init, because it's missing the method len. And len is one of the methods in the sort interface, right? So let's see how to do this. We implement a new method, which is func_len. This gives us back an integer, and of course this method is valid for patient queue. And then what this returns is simply the length of the dereferenced patient's queue. Okay, so the length of the slice that the pointer points to. Now that we have this, so just to clarify, this is required len required by sort interface. Okay, pop is required by the heap. Push is also required by the heap interface. Okay, so these two are belonging to the heap interface. This is what we're trying to satisfy, this requirement. And here we're trying to implement the length method. The sort interface. So now we need to continue with the sort interface. It needs two more methods. These two methods are func, again, on patient queues, swap, and we have positions A and B, which are integers, and then patient queue of A and patient queue of B is essentially patient queue of B and patient queue of A. And one thing I forgot here is that the patient has to have also an index property. This is just required by the heap interface. Okay, so, we save this. So the patient has name, severity, and index. We need to assign the indexes here. The index for A is simply A, and the index for B is simply B. No, dot index. Okay, so we have finished with the swap. This is also required by the sort interface. So now we need one more method in order to complete the sort interface requirements. That method is called less. Func less between two positions, and it returns a boolean. What this returns is the severity is less than the, so basically you are comparing patients from two positions, less required by, so what this method does is it takes two positions and then it compares two elements in the queue, element at position A and element at position B. So you tell it exactly how to evaluate that one item is less than the other. The problem with this is that it gives us a minimum heap. So what we want is a max heap. So we are going to flip this and we are going to say, give me the elements where severity of A is greater than severity of B. We flip the comparer So by flipping it, we achieve this requirement. All right, so now we have satisfied the sort interface. We have the 3 methods required by it. And then we have satisfied the heap interface, which needs 2 methods, push and pop. Now we can actually go back to our heap. We can now say, this is what you initialize the heap with. You initialize it with the patient's queue. Basically, now we just need to return the ER. The idea is that we can use some helper methods because we have this emergency room here, and we want to, we want to admit patients, and we want to handle the patients. So let's make some helper functions. So let's say func admit patient. It receives a patient, which is, an interface, and oops, this is for emergency room. I could have just as well said, this is a patient, pointer to patient directly, but I want to show a trick. So if we have an interface, how can we cast to a patient? So we can do this. Patient, potential patient is patient dot parentheses and a type, and we want pointer to patient. What this is a type assertion. Now that we have this patient, use the heap to push the patient into the emergency room. So then we say er.patient's queue and then potential patient, right? Adds new patients in ER. We also want to be able to handle the next patient. So let's have a function, func handle next patient, and then, it returns that patient. This is for emergency rooms. So then how do we do this? Well, then we say, first of all, next patient is heap.pop, right? So as you can see, we have these methods on the heap. So the heap is the one that handles the heap invariants. So all we need to do here is to use the methods available on the heap, and then we just pop from the patient's queue, and then we just return this. We return the next patient, as we learned here, as an assertion of type pointer to patient. We return this. We should also handle the case when there is nothing in the patient's queue. If the length is 0, return nothing. Remove highest prior from the queue. Let's say you have some scenarios sometimes when in the emergency room somebody was admitted with some status. Let's say was feeling good, but then all of a sudden that person feels a lot worse and it needs to be handled immediately. So let's say we have a function called update patient status, right? So then we have a patient, and then we have a new status, severity status, and this function is available for emergency room, of course. So basically what happens here, patient.severity equals new, right? But this is really important to understand. So what happens here when you change the priority of an item, remember that the heap is a heap because it satisfies a heap property. And the heap property is in a max heap. Each node has to have a value, greater than the value of its children. But when you go and you just update the value of some element, some random element, you have basically invalidated the heap property. We risk not having a heap anymore. And how do we restore the heap property? The heap interface has a method called fix. And what fix does, as we can read here, fix reestablishes the heap ordering after the element at some index has changed its value. We need to say fix queue by using the patient index. Now that we have written all this code, it would be nice to actually see if it works. So let's close some files here. Now let's go to our test file. Let's say package, and let's write some tests. So let's say we are first testing this priority queue when it's literally empty. So func, we start with an edge case. So we have test the priority queue. If we pop when the queue is empty, it should not crash. Bit of a long name, but should be explanatory. So in the context of a new emergency room, if we try to pop an item, so we handle the next patient, we have a handling here in this method. If there is nothing, then return nil. Let's test this. If next is not nil, then we have an error. Expected empty CQ to return nil. Let's see if the test is working. Go test. It's working so far. Now, let's say we have 2 patients, and then we should return them in the order of their severity. So not FIFO, but in the order of who's feeling worse. Test prio Q when 2 patients return highest prio. So if we have a new emergency room, so let's say we admit 2 patients, admit patient, and we have a new patient with the name, John. John is feeling not so bad, but he's there for a reason, so he knows why. Then we admit another patient, and let's say the name is, I don't know, Sam. Sam is feeling pretty bad. Then we would expect that even if Sam was admitted after John, he should be handled first because his severity is critical. So let's see that. So the next patient that is handled is the next patient. If the next one is not Sam, then our whole emergency room is doing something wrong. Expected Sam to be the next handled patient. Go test. Right, and what happens is that the test is failing. Let's see why the test is failing. Interesting. So if we go to handle the next patient, we are returning. Then we have heap.pop. Then we go to our patient's queue. This is exactly why it's failing, because we have not written the implementation for pop. So we have implemented only the sort. First of all, to push an item, the heap interface demands that the argument is of interface of any type. So we need to transform this into an actual patient. So the data, patient data, that's why I called it patient data, not patient, because it's not yet a patient. We are going to make a type assertion here, and we are saying, yeah, this is a patient. But then we need to also assign its index to the length of the slice behind the patient's queue. This is only required by the heap interface. And then what we need to do is we need to add the new patient to our slice. Remember that this, PQ is a pointer. So if we dereference that pointer, the slice behind it will be append to that slice the patient. This is essentially the adding of new elements. All right, now let's solve the pop. The pop method is required by the heap interface as well as the push. Let's delete this because we no longer need this comment. First, we store a reference to the current queue is the slice, and then we store a reference to the length of the current queue, and then we need to remove the last element because that's what pop does, removes the last element. Then we say patient is simply current queue of the length -1, right? And now that we have extracted it, we can say, index is -1, again, required by the heap. And then we simply need to reassign the slice to no longer contain the last element. So then we dereference this pointer and we say, this is now current queue from first position until the one before the last. So then we just return the patient. Now we have solved the pop method. So essentially we have now finally completed the full implementation. Let's redo our test. As we can see, now the test is passing. We remember that we also have a method called update patient status. So let's write some tests that make sure that this method also works, because we are doing something interesting here. Remember that we are changing the heap by updating the severity of the patient. Since this severity property was the deciding factor for our heap, we need to fix the heap. So let's see if this whole construct even works. So let's write a test function, test prio q after update patient status turn highest prio. Okay, t testing the t. In the context of a new emergency room, let's say we admit a patient called Diana and Diana is feeling reasonably well, has a mild injury though, and then we admit, let's say we have a patient called Liam and severity is also, and then we admit Let's say we admit another patient. Say this is also a new patient by the name, I don't know, whatever, Jamal. And then severity is mild as well. So all these patients are feeling fine. But all of a sudden, update patient status, Liam is feeling really bad. And the ER handles the next patient. And if the next one is not Liam, then our emergency room is not exactly an emergency room. So if not, go test. It works. Diana is also feeling a little worse, moderate. Next to is ER that handle next patient. So if next to that name is not Diana, then we have something wrong in our emergency room, right? So as we can see, it's working. And finally, Jamal, who patiently waited for the other two patients to be processed, and finally now has his turn. So the last one is next 3 is ER that handle next patient, and this should be Jamal. If it's not so, let's see, go test. As you can see, our emergency room behaves as expected. We have, I guess, maybe saved some lives with our wonderful priority queue. That was it. Thank you. Comments down below. All right, if you enjoyed this video, please subscribe and I'll see you next time. Thank you.